All right, so we're going to finish up our 5.2 class notes. So last time we finished A and B of example 3, prove the following identities. So now we are going to do C, D, and E. All right, so let's talk through and work through proving this trig identity here. Now, the left and the right side both look very similar, and so they're kind of both equally complex. So I'm going to start with the one on the left. So we'll say tangent of x all over secant of x minus 1 equals, now in this case, the fact that I see secant x minus 1 here and I see a secant x plus 1 up here leads me to think, how about I multiply, all right, so I'm just going to rewrite this right now, tangent of x all over secant of x minus 1. What would happen if I multiplied by secant of x plus 1, because that's what I want in the numerator, and secant of x plus 1 down here? What's going to happen in my denominator? Well, I'm going to get a secant squared. Hey, secant squared and tangent squared are related in a Pythagorean identity. So I'm not going to multiply the numerator out right now. I'm just going to say this is tangent x times secant x plus 1. And here I'm going to get secant squared x minus secant x plus secant x cancel, and then minus 1. And sure enough, secant squared x is equal to tangent squared x plus 1. So if I subtract 1 from secant squared x, that gives me tangent squared x. And thus, tangent of x up in my numerator will divide out. Secant of x plus 1. And that is rather messy, so I'm going to write this a little bit better. And, right, tangent and tangent squared, simplify away, and I get exactly the right side. Secant of x plus 1 all over tangent of x. Check. Identity proved. All right, how about this one? So, D, tangent squared x minus sine squared x equals tangent squared times sine squared of x. That's interesting. So what can we do here? Well, let's start by rewriting tangent squared x. I'm going to rewrite everything in terms of sine and cosine. So I'm going to start with tangent, I'll start with tangent squared x minus sine squared x. And I'm going to say, well, this is sine squared x over cosine squared x. That's the definition of tangent. Minus sine squared x. So to get a common denominator, I'm going to multiply this piece only by cosine squared x over cosine squared x. And then that's going to give me sine squared x minus sine squared x times cosine squared x all over a common denominator of cosine squared x. So up top, I notice I can factor sine squared x out of the top and the bottom, right? So this is going to equal sine squared x times 1 minus cosine squared x. And that's all over cosine squared x. Now here, right away, sine squared x over cosine squared x, that's exactly tangent squared x. That's what I want. So I'm going to put that. First, I'm going to, since I didn't give myself a ton of room here, I'm going to rewrite this further over on this side and say, all right, so that's sine squared x times 1 minus cosine squared x all over cosine squared x. So I can say, hey, that is tangent squared x times 1 minus cosine squared x, right, all over 1, right, which I don't even technically need. And what is 1 minus cosine squared x? That is, again, my Pythagorean identity. Cosine squared x plus sine squared x equals 1. So if I subtract cosine squared x from 1, that leaves me with sine squared x. So tangent squared x times sine squared x. Check. Identity proved. Who would have thought something minus something else is equal to the product of those two things. Isn't that cool? I think that's cool. All right, E, let's prove E. Tangent to the fourth x plus tangent squared x is actually equal to secant to the fourth x minus secant squared x. All right, so let's go from here and see what we can see. All right, the fact that I've got 4 powers and 2 powers here, well, first off, let's start with tangent to the fourth x plus tangent squared x. I'm going to rewrite this by first factoring out a tangent squared x. I'm going to say tangent squared x times tangent squared x plus 1. Do we see that? So this is, again, tangent squared x times tangent squared x because it's to the fourth power. So this is equal to this. Well, what's tangent squared x plus 1 equivalent to? That's just secant squared x, right? That's one of our trig identities. And then tangent squared x, if I wanted to rewrite that in terms of secant, right, so again, I know secant squared x is equal to 1 plus tangent squared x. So tangent squared x is going to be secant squared x minus 1. That's what this guy's equivalent to. Times this is just secant squared x. And so when I multiply them together, I get exactly what I was trying to prove. Secant to the fourth x minus secant squared x. Check. Alrighty. So, believe it or not, that's all I really had planned for 5.2. So I'd like you to do the 5.2 homework, get a head start, practice doing some of these, and then when we meet together in class, we'll continue on and pick up from here. Since I feel like this has not been a full class time, I wanted to go back to your 5.1 class notes, right? So if you feel totally good with 5.1, you have my permission to stop watching. If you'd like to see how we would have finished out, example 14, practice solving these equations, keep watching because that's what we're going to do right now. So 5.1 class notes, this is example 14 is where I'm going to start. And let's work through these. So determine all the real solutions for the following equations. Alrighty. 2 times sine of x squared plus 3 times sine of x equals 2. Well, that's the same thing as saying 2 sine squared x plus 3 sine x minus 2, subtract the 2 from both sides, equals 0. And can we factor this? It's quadratic in sine. So if I have 2 sine of x times sine of x, that's how I'm going to get my 2 sine squared x. Negative 2, well, if I put a 2 here, that's going to give me 4 and 1. So if I want a positive, so I'm going to want plus 2, and I'm going to want minus 1. So what have we got? That means that 2 sine of x minus 1 equals 0, or sine of x plus 2 equals 0. So for this guy here, add 1, divide by 2. That means sine of x is going to equal 1/2. Where does that happen? On my unit circle, up here. So that's going to happen at pi over 6 and 5 pi over 6. So for all real solutions, my solutions are going to be x equals pi over 6 plus 2 pi n, or 5 pi over 6 plus 2 pi n, or what else? For this guy, sine of x plus 2 equals 0. That means sine of x would need to equal negative 2. Well, but when does that happen? Never happens, right? Because sine of x is always between negative 1 and 1. So this will never be equal. So these are our only solutions. Okay? How about this one? Okay. Secant squared x plus cosine squared x equals tangent squared x plus 5/4. Alrighty, so what can we say? Well, I see a secant squared and a tangent squared. So let's at least convert those, one of those into the other one. So I know secant squared x is equivalent to 1 plus tangent squared x. All right, and then I have plus cosine squared x is equal to tangent squared x plus 5/4. That's 1 1/4. So I'll just leave it as 5/4 for right now. No, I'm going to write it as a mixed number, 1 and 1/4, and you'll see why. Because now, well, if I subtract tangent squared x from both sides, that just goes away. If I subtract 1 from both sides, what am I left with? I'm left with cosine squared x is equal to 1/4. Okay. If I take the square root of both sides, that means cosine of x is going to equal plus or minus the square root of 1/4. Well, what is the square root of 1? It's 1. What's the square root of 4? 2. So where is cosine of x equal to plus or minus 1/2? Again, plus or minus, that means I'm in all 4 quadrants. And when is cosine equal to 1/2? That's here and here. So that's there, there. So what are my reference angles? This is my 60° or pi over 3. So that's going to be x is pi over 3. And this is actually interesting because this guy is just pi more than pi over 3. So I don't have to list all 4 of these with a plus 2 pi n. I can in fact just list these first 2, pi over 3 plus pi n, or I'll just put a comma, or 2 pi over 3 plus pi n, because, again, let n be 1. Pi over 3 plus pi is this guy over here. And let n be 1 here. 2 pi over 3 plus pi is this angle right here. So that's going to hit all of my solutions. Alrighty? So now if you continue on, these are more examples where I was just asking you to simplify. And so hopefully now you see why were we practicing simplifying? Because it gives us ideas of how we can manipulate expressions when we're trying to then prove identities. So let's simplify, let's manipulate these a little bit. What does this simplify to? Well, we can multiply this out, and that's going to give me cosecant x squared. Plus minus cancels out, minus 1. Ooh, I feel like there's a trig identity there. And this is cosine squared x. So what trig identity, right? Cosecant squared x is equal to 1 plus cotangent squared, right? And so cosecant squared minus 1 is going to be cotangent squared x all over cosine squared x. Well, cotangent is cosine squared x over sine squared x, and that's all then being divided by cosine squared x. So again, that's like cosine over 1. So if you multiply by the reciprocal, this is all going to simplify to just what? 1 over sine squared x, which is, by definition, cosecant squared x. So that's how that guy, that is how that simplifies. So for instance, if you were asked to prove the identity that this is equal to this, that's one way you could do it. By the way, worked out solutions for this, since I'm not going to do them all right now, so you know, if you scroll down, 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 here they are, right? So if you want to see more practice worked out step by step, please do. I would encourage you right now on your own, because you still have time, pause the video and or just stop the video and do example 16, 17, right? 18. Simplify, manipulate these expressions, and see if you end up getting the same thing that I ended up getting. And then again, at the very end, there's more additional notes and practice problems. Feel free to practice and review. Make sure you have your identities memorized, right? And again, just a few more problems for you to practice on. So that's it. I'll see you guys in class.